All right, everyone should have gotten a new kind of note packet for this next unit. Bless you. This next unit, much like the first unit we did, is fairly long. Okay, so the unit test you guys actually took yesterday was the first half of Unit 2. We're going to now transition into the second half. So the content that we cover in this continuation unit isn't really going to be new. We're going to be building off of some of the vocabulary and ideas that we've been working with so far, like multiplicities, x-intercepts, synthetic division, factoring. You're going to see a lot of that over again. We're just going to go a little bit deeper. So we're going to kick off on page 173, and we're going to take a look at some things that we've discussed about graphs in terms of characteristics. Might not necessarily always be true. Okay, there are some like kind of tricks or things that we need to be aware of, or some things that might be a little bit weird. We're going to talk about those weird things. So if you take a look on page 173, and you first start to read like the little paragraph at the top of the page, it says the degree of the polynomial function identifies the number of roots, aka x-intercepts, aka zeros, okay, all those synonyms that it would have. We've already discussed that. Didn't we say how, like, if we add up all the multiplicities from the x-intercepts, we would get the degree? Okay, that's what that's referring to. However, not all of the roots, aka zeros, aka x-intercepts, have to be real roots. Do you know what they mean by real roots? Yeah? They could be imaginary. Okay, so whenever you see the word real root, or the word real in a math class in general, it just means that it's graphable. Like it'll show up on a picture. So we're going to investigate this today. All of the graphical characteristics that we've done up to this point have been real. We've been able to pinpoint on a graph, okay, specific spots, specific characteristics, specific locations. But what we're going to get into now is how can we determine if there are some imaginary properties, okay, things that we can't really see on the graph. Okay? You can just leave it there if you're done, okay? All right, so it is possible that some of the roots could be imaginary, and we're going to see that in this case. So take a look at this kind of first graph here. Can you tell me what type of graph this is? What type of polynomial? Can you name it? Yeah. Cubic. Okay? So if we were to find the x-intercepts and add up all the multiplicities, we would get 3, right? All right? If you look at the graph, I only see one x-intercept. And what's the multiplicity of that x-intercept? Yeah, 1. Shouldn't they all add up to 3? Okay, so what do you think that's telling us? We have one real root. Okay, you can graph it, you can see it. It's plotted right there. What about the other 2? Because we know there should be 3. How do you think we would classify the other 2 roots or x-intercepts or zeros? If you can't see them, yeah. Say it again. They would have to equal 2. Like, we need 2 more, right? We know there should be a total of 3 because it's cubic. Right now we only have one x-intercept with a multiplicity of 1. So we're missing 2 of them, right? Okay, if this is the real root, you can plot it. What are the other 2 going to be called if you can't plot them, if they're not graphable? Yeah, imaginary. Okay, so we're going to investigate this idea a little bit further. We know we should have so many x-intercepts based off the degree, but how can we determine how many are real and how many are imaginary? Okay, so let's think about this. If the graph was shifted up or down, okay, if you were to like start to pinch this graph and move it up and down, what is the maximum number of x-intercepts that it could have? Could you visualize that if you were to move it? How many times would it cross the x-axis at most? What do you think, Maddie? 3, right, okay. Or instead of moving the graph, what if you thought about moving the x or the x-axis? instead of the x-axis being here, what if you moved it up here? Okay, you shifted it. Wouldn't it cross 3 times, right? Okay, so we'll say we'll have 3 x-intercepts, or 3 zeros in that case. So if the x-axis was up here, we would have 3 x-intercepts, and what are the multiplicities of all of those? Yeah, they're all 1. So if we did 1, 1, 1, and added all those up, wouldn't it be the cubic of 3 that we needed? Okay, so what we're doing here is we're still investigating these polynomial roller coaster shaped graphs. It's just instead of the x-intercepts showing up nicely on the x-axis, maybe the graph was shifted a little bit up or down. So we no longer have all of the multiplicities to take into account, okay, for those real x-intercepts. Maybe we have some imaginary ones that we need to consider. Okay, so we're kind of doing some shifting. Take a look at g of x. That's the next one down here. Okay, if you were to shift maybe the x-axis either up or down, at most, how many times would the graph cross it? Can you find it? You got it, Rebecca? 4. Okay, so if you started to shift up the x-axis, bless you, it looks like at most you would hit 4 times. So we would have 4 zeros. If you were to count the multiplicities, we strike through on all of those, so they would all be 1. AKA, we would classify it as quartic. Okay, but in terms of real x-intercepts versus imaginary, okay, based off this graph the way it looks right now, okay, no shifting necessary, we're just going to take a straight look at it. We have 2 x-intercepts, each with a multiplicity of 1, okay, so the multiplicities add up to 2, but we said that they need to add up to 4. So what would we classify the other 2 as that we're missing? We have 2 real ones that are graphed. The 2 that are not graphed are referred to as, yeah, say it again? Imaginary. Okay, so we're going to get into some imaginary x-intercepts. All right, so let's take a look at this idea a little further, this imaginary. Based on the graph, identify the number of positive, negative, 0, and imaginary roots. So if we take a look at f of x, this first graph, how many x-intercepts are positive? Meaning how many are showing up on the right-hand side of the x-axis? Yeah. Are you sure? Does this graph cross the x-axis anywhere over here? Not yet, okay? So f of x has 0 positive x-intercepts. How many x-intercepts does it have that are negative, meaning showing up on the left-hand side? Yeah? Just 1, okay, right there. How many x-intercepts does it have that are 0? Okay, meaning crossing right at the origin. Yeah, 0, okay. How many imaginary does it have? We said f of x was cubic. Okay, we had an x to the third. Yeah. It would need to have 2, right? Okay, if we added up all of those possibilities, aka multiplicities, we would have to get 3. But right now we only had 1 taken into account for, so that means the other ones that we're missing would have to be imaginary. They're missing because they're not graphable. Okay, they're not on the picture of the polynomial itself. Let's try the same thing for g of x. How many x-intercepts are positive, meaning showing up on the right-hand side? Yeah, 1. How many are negative, showing up on the left-hand side? Yeah, 1. How many show up right at the origin? Good, Grace. 0. All right, we said g of x was quartic, because if we shifted the x-axis a little bit, it would touch at most 4 times. Okay, but the x-axis is not located somewhere up here. It's located down here. Okay, the graph was shifted a little bit. So instead of having those nice x-intercepts like we've had up to this point, they're no longer there because we did a little movement. So we need 4, and right now we only have 2, so that means the other 2 have to be imaginary. We doing okay? Making sense? Okay. What about the left and right end behavior? This is kind of a review for us. It's nice that we have the pictures to go off of. Can you describe how the graph behaves on the left and right hand side? Maybe for f of x. Go ahead, Maddie.
For f of x, left hand side falls, right hand side rises.
All right, so left falls, right rises. If you wanted to use the mathematical notation, like as x does this, then y does that, that's okay too. If you want to be kind of a little bit more abbreviated and say rises and falls, that's fine. Okay? You just got to communicate your point across. What about g of x? Left and right end behavior? Yeah.
Left falls and right falls.
They both fall. Good. Alright, let's try to check this out. So now that we identified the type of equation, okay, f of x is cubic, g of x is quartic, and we know something about the end behaviors, let's think about that leading coefficient. Okay, if we had an equation in standard form, that very first number out front, would it be positive or negative? Okay, so can you reason through what the leading coefficient might be for either one of those equations? What do you think? Yeah.
For the first one, for f of x, it would be a positive leading coefficient.
How'd you know?
Since the right end behavior is going up.
All right, so if you look at the f of x graph, the right end behavior we said rises, it's going up. Okay, the right side dictates the sign of the leading coefficient. So using that logic, what do you think g of x might be for its leading coefficient? Yeah?
It would be falling
Mhm.
because the right end behavior is falling.
All right, so if the right end behavior is falling, then this leading coefficient would be negative. Perfect. We did that on the last test yesterday, right? We did very well, by the way. Scores are in, so if you want to check and see how you did, you can. Not everyone has taken it, though, so you'll get it back once everyone finishes it. Okay? All right, let's talk about some factors. Okay, maybe we wanted to start develop the equations of these two graphs. Based on the graph, what factors are guaranteed to be in the equation? All right, so take a look at f of x. If we wanted to write a little factor parenthesis group in the equation, what might it look like? Where do the factors come from? Yeah. The x-intercepts. All right, so we said we had one x-intercept on the f of x graph. What would the factor look like? Yeah. X plus 4. Since that is the only x-intercept, that's the only factor we are guaranteed to have. Okay, there might be some other ones, okay, imaginary ones, right? But this is the only one that we are guaranteed to have based off the graph. What about g of x? Yeah.
X plus 3 and x minus 3.
X plus 3, x minus 3. Based off those x-intercepts. There might be more. There might be imaginary ones, okay? But those are the only ones that we're guaranteed to have based off the equation. All right, and big throwback here, what about domain and range? So if you were to drag your pencil left to right, low to high, can we pinpoint domain and range for these two graphs? What about f of x, the one at the top? Yeah. Okay, so you could use that interval, negative infinity, positive infinity. Maybe you want to use the double-stemmed r, all real numbers. Good. What about range, if you did low to high? Dragging your pencil. Good, Maddie? Same thing. All right, looks good. What about g of x? Drag your pencil left to right for the domain. Good, Maddie? Same thing. All right, range, low to high. Good, Marie? To 5. All right, brackets or parentheses? Parenthesis, then bracket. Yep, good. Your graph stops at 5, and you can touch it there. You have some closed points, happen to be maximums. So far, so good. We doing okay? All right, so this first section, we're going to investigate a little bit further, okay, this idea of positive x-intercepts, okay, which ones show up on the right-hand side, negative x-intercepts, which ones show up on the left-hand side, 0 x-intercepts, which ones show up at the origin, and then those imaginary ones. Okay, the ones that are still there, we just can't see them. Okay, they're not graphable in this case. All right, so to bring in this idea, we're going to discuss something called the fundamental theorem of algebra. Do you guys know what that word fundamental means? I'm sure you've heard of it. Do you have any idea what it means, though? Yeah? The foundation. Good. Were you going to say something? Yeah? The basics, the foundation. It could also mean like important, the fundamental, like the fundamental skills or important skills of something, either a sport or a trade. So you guys are in pre-calculus, right? You've gone through pre-algebra, algebra 1, algebra 2, geometry, okay? And right now, okay, at this point in your mathematical career, we're just learning the basic foundation of algebra. Okay, it might seem a little strange, but this is what, at least in terms of historical mathematics, okay, people way back when with crazy hairdos and clothing, when they were investigating or creating mathematics, this is the first thing that they noticed. And that's actually what we're going to discuss about these x-intercepts. So the fundamental theorem of algebra is the basic concept that we already know. We just never referred to it as this. The fundamental theorem of algebra is the idea that a polynomial of degree n, okay, whatever degree you want it to have, cubic, quartic, quadratic, quintic, whatever, will have n roots. So if you have a degree of 4, you're going to have 4 roots. They might be positive, they might be negative, they might be 0, they might be imaginary, but you're going to have 4 of them. Okay, basic idea. Seems basic, but yet it took us this long to actually get to talk about it. You didn't talk about this in pre-algebra, algebra 1, algebra 2, geometry, anything like that. All right. So the roots could be, like I said, they could be positive, they could be negative, they could be 0, or imaginary. So the person that actually developed this fundamental theorem of algebra, maybe you've heard of him before if you're kind of familiar with historical mathematics. He's called René Descartes. I think he was French. I'm pretty sure. Okay, René Descartes. And he created a lot of things that we use today in terms of mathematics and algebra. But what we're going to credit him with, at least in this section, is his rule of signs. Okay, he kind of developed this process, this method to help him determine how many x-intercepts are positive, how many are negative, how many are 0, how many are imaginary. Okay, and that's what we're going to kind of discuss in this section. So just as a little brief definition, we're going to write it down. Okay, it might go over your head a little bit, but we're going to discuss it a little bit further. That way it starts to sink in. Okay, so his rule of signs said that the maximum number of positive roots is the number of sign changes in the f of x equation. So we're going to take a look at a polynomial equation in standard form, and we're going to basically just count how many times we go from either positive to negative or negative to positive. Okay, kind of simple. And whatever that number is, okay, that's the maximum number of positive roots. Okay, how many x-intercepts we might have on the right-hand side of a graph. Very similarly, okay, he noticed that the maximum number of negative roots is the number of sign changes in the equation f of negative x. So, bless you, if we were to substitute in negative x for all the x's and simplify it, we're going to count the sign changes in that new equation and see how many we have. That's going to dictate the maximum number of negative roots. Okay, how many show up on the left-hand side of a graph. Okay, so we're going to briefly just kind of take a look at how this works. Okay, how did he notice this? How did he go about using this rule of signs to help him determine? Remember, they didn't have calculators way back when, so all they had to work with was either graphing by hand, which definitely takes some time, especially if you want to do it accurately, or working with equations. Okay, so calculator might not be used a lot in this section, but we are going to use it just to help us out a little bit later on. Let's go ahead and look at this equation. So we're going to say p of x is this polynomial we're looking for. Let's just go ahead and practice finding p of negative x. Okay, if you were to substitute in negative x for all the x's, what would it look like? And you may have to think about your power rules for a little bit because we have a lot of different powers or exponents to work with. If you were to substitute in negative x for the first one, and then you raise it to the fourth, negative x times negative x times negative x times negative x, what are you going to get? Yeah. It's a positive x to the fourth, okay? So this first term actually isn't going to change. At least in terms of its sign, it's not going to change. So that one's going to stay a 2x to the fourth. What if you plugged in a negative x into the next term? Yeah. It would change to negative in this case, because notice how it was originally positive. So we now need a minus x to the third. What about if you plugged in a negative x into the next x? Yeah. It would stay the same, because if you square a negative, it becomes a positive, meaning your term is not going to change at all. If you plug a negative x into the next x, that would change to negative. And last but not least, we don't have an x to plug in there, but we still have that constant of 3. Do you guys notice a pattern at all with plugging in that negative x? Like which terms changed and which ones didn't? Maybe a little shortcut we can use in the future if needed. Yeah. All the odd degrees change. Okay, so when it comes time to figure out this p or f of negative x, whatever the function's called, all of the odd powered terms are going to change sign, whereas all of the even powered terms will remain the same. Okay, a little shortcut if you want to make note of that. All right, so now that we have p of x, okay, the original equation, and p of negative x, okay, this new equation, let's go ahead and try to determine, based off of Descartes' rule of signs, how many positive x-intercepts we might have and how many negative x-intercepts we might have. So the p of x equation, if we just copy it down from the top, is this long polynomial. And just like you read a book, just like you read a graph, we're going to move left to right. If you go from 2x to the fourth to x cubed, did you change signs? Did you move from a positive term to a negative term, or a negative term to a positive term? They're both positive, right? This is a positive 2x to the fourth, and then this is a positive, you see the plus x cubed. So this is not a sign change. Okay, they're both positive. What if you move from x to the third to the minus 8x squared? Is that a sign change? Yes, you go from a plus to a minus. What about between the next two terms? I think that's another yes. We go from a minus to a plus. And between the next two terms, both are being added, so that's not a sign change. Okay, so based off the original equation, we identified 2 sign changes. Yeah.
Should it be negative 2x?
Sorry, this is the original equation.
Okay.
Okay, it's okay. We're going to do the other one here. Okay. All right, so in the original equation, we have 2 sign changes. This is telling us that the maximum, okay, the maximum number of positive real roots, okay, graphable ones, ones that you can actually plot, okay, that it could have. I'm not saying it does, I'm just saying it could. That's the maximum number. You will not have more than 2. You might have less than that, okay, but you will not have more than 2. Let's try the p of negative x sign changes. So that would be our new equation, 2x to the 4th minus x cubed minus 8x squared, and keep going. Okay. Let's count our sign changes. Looks like we start off with 1 right off the bat. The next 2 don't change. The next 2 don't change. But the last 2 do. So it looks like we have 2 sign changes again. Okay. Are we doing okay with the sign changes? Can we visually see those? Okay. Now since this was p of negative x, this is kind of the negative equation we're working with. This is signifying the maximum number of negative real roots. Okay, how many x-intercepts we have on that left-hand side that we could have. Okay, again, you might have less, but you will not have more than 2 for this particular equation. Okay, for this graph. All right, now there is a way that Renee kind of discovered here how we can figure out the other combinations. Because notice how this word could have is kind of vague, like maybe you could have less than those since these are maximums. So I want you to just take a second and read this little short paragraph. See if it sinks in a bit. Alright, so let's take a look at this p of x equation, the original one, okay, aka the one that's representing the positive roots on the right-hand side of a graph. We said that since there were 2 sign changes, we could have at most 2 x-intercepts on that side. But what's another possibility? Yeah. How'd you get 1? It can be less than 2 by how much? Any multiple of 2 less, I guess I should say, than this maximum. Okay? So if you did minus 2, basically, 2 less than 2, we would have 0. Okay? Same thing's going on, or the same property applies to the negative equation. Okay? This should have a little negative sign in there. I forgot to type that in. So if it's the negative equation, the negative x we substituted in, that's representing how many negative x-intercepts we have, okay, on the left-hand side. We said that since there were 2 sign changes, we could have at most 2, or some other possibilities, if we did 2 less than that, we would have 0 again, right? So based off of this, we either have 2 on the left-hand side, or we don't have any. Okay, and then the positive ones are telling us we have 2 on the right-hand side, or we don't have any. Those are the only possibilities. Okay, so we're going to use Renee's rule of signs to help us with the positive and negative x-intercepts. We can also talk about those 0 x-intercepts, okay, the ones that kind of show up at the origin. These are going to be a little bit easier for us to do because we're going to use factoring to help us out, and I know we're pretty good with that so far. So just in terms of practice, let's go ahead and factor some of these polynomials. What do you feel like doing for the first one? Think about your different techniques. Yeah. Let's take out an x. All right, GCF, so we're left with x squared plus x minus 2. Can we keep going? Yeah. Okay, so 1 times negative 2 is negative 2. We got to add to 1. So two numbers that multiply to negative 2 but add to 1. Yeah. Negative 1 and 2. Perfect. All right, can we list the x-intercepts based off those factors? Where would those x-intercepts be located? These are real ones. Okay, we should be able to plot these. Yeah. Negative 2 and 1. And doesn't that make sense based off the graph they give us? We have 0, negative 2, and 1. So far, so good. Okay. Based on the factors, though, how many times, aka multiplicity, how many times is the x equals 0 a root, x-intercept? Can you tell based off the graph? Can you tell based off the equation what the multiplicity is? Yeah. Okay, so if you have a graph, notice how it goes straight through, so that's a multiplicity of 1. How can you tell based off the factor that it shows up once? Where do the multiplicities show up in terms of the factors? Yeah. The degree or the power, okay, on that x that we pulled out is 1. Okay, so we'll say multiplicity is 1. So it only shows up once. All right, let's try the next one at the top. Think about your factoring techniques. Yeah. X squared. So we're left with x minus 3. I don't think we can factor any further, so based off those factors, what real graphable x-intercepts do we have? Yeah. 0 and 3. Hopefully it makes sense based off the graph. Okay, we can plot them. So how many times is 0 a root? Yeah. How did you know?
Since it bounces off the x-intercept.
All right, graphically it bounces. Based off the factors, do you see how it has a power of 2? Okay. So multiplicity of 2. AKA it shows up twice. All right, what about our last polynomial? How do you want to factor it? Yeah? Grouping. Good. We have 4 terms. All right, so GCF out of the first group looks like an x squared. So we're left with an x plus 1. What can we GCF out of the second group so that we're left with another x plus 1? Yeah. Negative 4. All right, so our two factors, x squared minus 4 and an x plus 1. We're done with the grouping, but can we keep going? What do you see, Marie? Yeah. All right, we got a perfect square right there. Difference of perfect squares. So we'll have an x plus 2 and an x minus 2. And then the last x plus 1 factor. So based off of those, looks like the x-intercepts that we can plot are negative 2, positive 2, and negative 1. Graphically speaking, making sense. How many times was 0 a factor? How many times was it an x-intercept? Yeah?
2.
How'd you know?
Let's say there's a
There's no group. Okay, notice how in terms of the equations or the factors, the only way you get an x-intercept of 0 is if you have kind of a lonely x out front. Okay, sometimes there might be a number out front of it, like a 4 or 2 or something, but in terms of these factors that we just did, we don't have that lonely x out front, so we're not going to get that x-intercept of 0. You can also tell graphically, right, because this graph never ever crosses the origin. Okay, so it doesn't have a multiplicity. Okay, it's not showing up at all, meaning it's not a factor. Okay, so let's go ahead and maybe bring a connection or relationship to these 3 graphs that we just looked at. 2 of the 3 functions have something in common, both graphically and analytically, that is different from the other function. What are these differences? Okay, so maybe take a look at the equations at the top. Do you notice anything different about these 2 equations we had here that had a 0 as an x-intercept versus this equation that we said didn't? Yes?
The 2 that got the 0 you can factor.
You could pull an x out of it. Okay? So we will say f of x and g of x. Okay, those are the first 2 at the top, because notice how the third one's labeled h of x. F of x and g of x have the variable x as a GCF. Okay, you are able to factor one out, whereas in h of x you weren't. Okay, not every single term had an x in it. Because if you look at h of x, the very last term is constant, right? It's just a -4, there's no x there. So x is not a GCF, okay? So if you do have a GCF of x, you know you're going to have some type of x-intercept at the origin, because you're pulling that x out. All right? Based on what you've seen, how will you determine the number of times that x equals 0 is a root? Yeah? The degree of the x. Okay, so we'll say when x is factored out, its degree or power, whatever word you want to use, is the multiplicity, aka how many times it's a factor. Alright, so to just look at the top again, to kind of reiterate this, we were only able to pull out one x from all the terms, so that's what the multiplicity was. In the second graph, we were able to pull out 2 x's from all the terms, so that's what the multiplicity was. Okay, so how many x's you can factor out, that's how many times that x-intercept is going to show up at the origin. Okay, so let's take a look at this. This was the p of x equation that we just kind of looked at for the Rene-Descartes rule of sign changes. Okay, is it possible that any of the roots from this equation are 0? How can you tell just by looking at the equation? What do you think, Marie? No, because x cannot be factored, x is not a GCF, however you want to phrase it. Okay, so we know just by looking at that equation, since we cannot pull out an x, it will never cross at the origin. Okay, it does not have an x-intercept there. Which means they're either all to the right, all to the left, or some are to the right, some are to the left, and maybe some are imaginary. So the whole idea with these 0 origin x-intercepts is if you can pull an x out. We doing okay? Alright, so we looked at positive and negative with the Descartes rule of signs. We just looked at the 0 ones. Okay, tomorrow we're going to look at imaginary x-intercepts, the ones you can't graph, and then we're going to kind of bring everything together to look at some example problems. Okay?